Alrighty then, corn children, children of the corn. Today's lesson, limits at infinity and horizontal asymptotes. Now, if you have not done the lesson on dominant terms, you need to stop this video and go back and do those lessons, because I will be discussing dominant terms in here. And if you don't know what they are, well, there you are. All right, limits at infinity. Consider with me the following. Beep. What is the limit as x approaches infinity on the function 2 to the x? Now, for your learning enjoyment, I have drawn for you the function 2 to the x. It's an exponential function. It goes through 0, 1. What are we doing? Here's what we're doing. We are instructed to walk x towards infinity. Here's your x-axis. That way is infinity. So you are walking on our function, and you have been instructed to walk that way. X goes to infinity. When do you stop walking? Never. It's infinite. So how do we answer this? The answer is the y coordinates as a result of the instructions in the x coordinates. Well, what happens as we walk to the right infinitely? This gets higher and higher and higher and higher. And the answer here is positive infinity. The limit does not exist. It goes off to positive infinity. So you might be saying to yourself, well, that makes sense. If this is infinite, that's infinite. Whoa there, Nelly. All right, let's look at another example. Are you thinking right, though? All right, here's our next example. Again, what is the limit as x approaches infinity? And this time our function is the mother of all parabolas flipped over. There's a negative in front of it. Yes, I've drawn it for you. Now, once again, we've been told we must walk this way. So you are going to walk on the function. Here you are. It's steep, I know. Hold on. And you are walking that way. As you walk that way, what are your y coordinates doing? Well, they're getting bigger and bigger and bigger in the negative direction. So now, yeah, okay, so when these are infinity, these are either positive or negative infinity. Whoa, back the bus up. Beep, beep, beep. Consider with me another example. I know, right? All right, here we go. This is the limit as x approaches infinity of our parent function 1 over x, the rational function. Yes, I've drawn it for you. So now this time, again, we are going to have to walk this way. These are our directions. The directions say, walk that way. Now this time, as we walk that way, what are the heights doing? The heights are getting closer and closer to a height of 0. No, yeah, we have a finite answer to an infinite limit. That's crazy. I know, it's fun, isn't it? So you can see here we have a lot of variety depending on the function. Why does this happen? Well, do you remember what we say about our rational function? It has a horizontal asymptote, doesn't it? As a matter of fact, abbreviating horizontal asymptote at y equals 0, this leads us to the definition, yes, that's right, the definition of a horizontal asymptote. Now, if you need to, you should probably pause the video, as of course you're taking notes, and you should write this down. All right, here we go. A horizontal asymptote. The line y equals L is a horizontal asymptote to the graph of f of x if, when you take the limit and send x to infinity for that function, you get L. L is a number, a real number. So if you have an infinite limit and it equals 5, horizontal asymptote, y equals 5. If you have an infinite limit and it equals 7, horizontal asymptote, y equals 7. So whatever this number is, that means you have a horizontal asymptote. Now, in these two cases here, where the answers were infinity and negative infinity, you don't have a horizontal asymptote. These are not numbers. That's infinitely large. All right? Hey, let's look at some more examples with these limits as x goes to infinity. Oh, I'm so glad you asked. Here they are. All right, look at this example with me. All right. Now, this time, I have two terms, two functions. X is going off to infinity, and we have two terms. We just looked at 2 to the x. 2 to the x goes up and up and up and up. This term is trying to go up to infinity. Because of the negative, this is our downward facing parabola. So this term is trying to go down to negative infinity. It's like a tug of war. This one wants to go up, this one wants to go down. Who's going to win? Ladies and gentlemen, an analogy, if you will. All we have to do is figure out who the dominant term is. It's like a tug of war between me and J.J. Watt. Now, J.J. Watt plays in the NFL. He's a beast. So here's the idea. If we can just figure out who's who, we have the answer. This is where that dominant term lesson comes in. 2 to the x is a dominant term. This is J.J. Watt. And this is me. Dominant terms win. If there's a tug of war between me and J.J. Watt, it's not really a contest. All we have to do to answer this question is figure out who the dominant term is and which way are they going. The answer here is positive infinity. The non-dominant term, even if there's more than one non-dominant term, doesn't really play a role. It's overwhelmed by the other one. Interesting. Yeah, I know, right? Okay, well, let's look at a different kind of problem. This was two terms adding and subtracting. Okay, but what about when we have infinity divided by infinity? Oh yeah, that's crazy fun. All right, if you recall, well, let's backtrack 1 second here. Let's recall this example here. Do you remember this example? We talked about this in the past. We said that we could think of this as an analogy where the numerator is the number of pizzas and the denominator is the number of people. And the answer is how much pizza do you get? So you had one pizza, but you invited over everybody on the planet. Well, how much do you get if you have to cut up one pizza with everybody on the planet getting some? Well, you pretty much get nothing. So, hey, that went haywire. You pretty much get nothing. So again, pizza in the top, people in the bottom, how much do you get to eat? Nothing. All right. So we need to consider now the more complicated example of infinity over infinity. Okay, let's look at this example. What do you mean infinity over infinity? If you look just at the numerator, the dominant term is x cubed. So if x goes off to infinity, this x cubed would go up to infinity. All right. If we look at the denominator, the dominant term in just the denominator is x. The line y equals x. This would also go up to infinity. So I have an infinite number of pizza and an infinite number of people. How do we know what's going to happen? Well, it's very simple. Now, after we decide on who's dominant in the numerator and denominator separately, you compare them. It is more dominant to have x to the third power than x to the first power. We have a dominant term in the numerator. So even though there's an infinite string of people, each person gets an infinite amount of pizza crammed into them. The dominant term in the numerator means that this answer will be infinite. You want to pause right here, right now, and you want to write something in your notes, like when you have limits as x to infinity and the dominant term is in the numerator, the answer is infinite. Yeah, you can rewind it. I know, it's crazy. Dick. All right, let's try another one. Check out this example. Once again, in the numerator, the dominant term is 3x to the first. In the denominator, the dominant term is x squared. So you have an infinite number of pizzas, but at every single pizza, there's going to be an infinite number of people showing up. The dominant term for the whole problem is in the denominator. So the number of people will overwhelm the number of pizzas, and this will equal 0. Yeah, that's right. When the dominant term is in the denominator for a limit as x approaches infinity, the answer is automatically 0. Furthermore, if you recall the definition for horizontal asymptotes, that means the graph of this function has a horizontal asymptote at y equals 0. Oh. All right, so dominant in the top, dominant in the bottom. One more example. That's right, you may have seen this coming. Take a look. Dominant term in the top is an x to the first. Dominant term in the denominator is also an x to the first. These are what I consider at the same level of dominance. We don't have a clear winner. So what do? With limits as x approaches infinity. I'm not talking about x is approaching 4 or 9. X is going to infinity. What do? Well, when these are what I consider equally dominant, it is the coefficients 2 and 1 that become the answer. So, yes, there's an infinite number of pizzas, there's an infinite number of people, but because they're equally dominant, this is saying every single person is going to get 2 whole pizzas. And again, because the limit as x approaches infinity has a finite real number answer, that would mean the following. If we were to graph this function, we would see a horizontal asymptote at a height of 2. Booyah!